Hi, these notes are going to be about the gas laws and solving gas law problems. And in order to be able to do this, we need to be able to do some basic algebra. And so before we get going here today, I would like you to go ahead and try to do a little bit of gas law math for me, just solving some problems, solving for x. And so there are several problems here, 4 problems here I'd like you to go ahead and try solving right off the bat. 1, 2, 4, and 10. Please go ahead and do those. And then once you are done, go ahead and come back to the video and we'll put up some answers for you. All right, so hopefully you've done those problems and now you know that the answers for numbers 1, 2, 4, and 10 are listed there. Make sure you got them correct. If you did not get them correct, I'd like you to go ahead and try again or go back to rewind this video and look at some of the other problems and give some of those other problems a try as well. But the point is here that you need to be able to do mathematically all 4 of these types of problems in order to be able to be successful at gas laws math. If this is a difficulty for you or you are having problems with this, please make sure that you go ahead and come see me or your teacher during their Zoom office hours. All right, so that brings us to our set of notes for today. The topic for this is the gas laws. There is a set of Cornell notes in Schoology for you to use to take these notes and take them down. And so go ahead, please, and get that date and topic your notes, and then we'll be ready to proceed. All right, so we're going to talk about 4 gas laws, and each gas law compares what happens if you change one of those factors, pressure, volume, temperature, or the number of particles in a particular gas, and what happens to one of the other things as we go along. All of these 4 laws that we're going to talk about today were named after scientists that either discovered the relationship or were honored by having the relationship named after them. So we're going to start off with Boyle's law. This is our first law that we have. And what Boyle's law has to do with is volume and pressure. So the question that goes along with Boyle's law is, if we want to increase or decrease the volume of a gas, what will happen to its pressure and vice versa? Okay. So in Boyle's law, the 2 things that are changing are volume and pressure. The 2 things that are staying the same are the number of moles of particles and the temperature. All right, and so we can sort of think about it using this picture over here. If here's my particles that are inside a container, and if I go ahead and I lower the volume by pushing this piston down, you'll notice that the gas particles inside are now much closer to one another, and so they're going to start colliding with one another more, and if we have that, that means they're going to create more pressure. So as volume goes up, pressure gets smaller. As volume goes down, pressure gets bigger. If we were to graph that out, we would end up with a graph that looks something like this over here. And for those of you who might be more mathematically inclined, you might recognize that as an inverse relationship. As pressure goes up, volume goes down. As pressure goes down, volume goes up. And so mathematically, we can write an equation for that, where if we multiply the pressure and the volume before we change times the pressure and the volume after we change, those 2 things should be equal. So P1V1 equals P2V2. So here is our relationship again. They're inverse of each other. And so the idea is, why does that relationship hold? Why as volume goes down, does pressure go up, or volume goes up, pressure goes down? Well, if we have more volume, that means we have more space, so we're going to have less collisions. Less collisions means pressure goes down. If we have less space, we have more collisions. Again, that means pressure goes up. Okay. At this point, I'm going to ask you to pause this video, go into Schoology, and go ahead and take a look at the Boyle's law demo videos. You could also do this after all these notes as well. But again, Boyle's law demo videos, they're going to show you some work with a vacuum pump, where they go ahead and they change the pressure, and you can see the difference in a volume happen as a result. Here's an example of the kind of problem you might solve using Boyle's law. Okay, so it says Example says, at a constant temperature and number of particles, a gas has a pressure of 2.5 atmospheres and a volume of 4 liters. If the volume is changed to 5 liters, what is the new pressure? Okay, so to solve this, we are going to start with our equation, P1V1 equals P2V2. And so we're looking for a pressure. Oh, I see one right there. 2.5 atmospheres. And we're going to multiply that by the volume that goes with it, 4 liters. And we know that equals a new pressure, which we don't know. That's what they're asking for. And a new volume, 5 liters. So if I go ahead and I then solve this for P2, and the way that I would do that would be to divide both sides by 5 liters, because that's what we're trying to get away from the P2. That means my 5 liters cancel. And so I would be left with an answer of pressure 2 equals 2 atmospheres. Here's another example of a problem. At a constant temperature and number of particles, a gas has a pressure of 6 atmospheres and a volume of 4 liters. If you want to make the pressure be 12 atmospheres, what volume does the gas need to occupy? All right, so again, P1V1 equals P2V2. The first pressure is 6 atmospheres, and that goes with a volume of 4 liters. And it says we want to create a new pressure of 12 atmospheres, and they want to know what the volume is. So that's got to be V2. So just like on the previous one, to solve for V2, we're going to need to divide both sides by 12 atmospheres. Cancels on this side, and we end up with V2 equals 2 liters. The second gas law we want to talk about is Gay-Lussac's law, and this has to do with pressure and temperature. So the question that goes along with this is, if we increase or decrease the temperature of a gas, what will happen to its pressure, and vice versa? All right, and so for this particular one, what's changing? Temperature and pressure. What does that mean is staying the same? The other two factors, the number of particles and the volume. All right, so we can sort of think about this for a second. So if I go ahead and I start heating up some gas, that's going to make those gas particles move faster. That makes them move faster. That means that they're going to go ahead and they are going to collide more. And if they collide more, that means, and faster, that means that they're going to be colliding harder. And if they collide harder, we know that that increases pressure. So as temperature goes up, pressure goes up. As temperature goes down, pressure goes down. If we were to graph that, we would get a nice graph that looks like this, linear graph, and we call that a direct relationship. Translating that into a mathematical equation, the equation for Gay-Lussac's law is P1 over T1 equals P2 over T2. So once again, to help us explain why, we simply say when the temperature goes up, there's more speed, right? So temperature up, more speed, temperature down, less speed. If that's the case, there are more and stronger collisions if the temperature is up, so that's going to cause my pressure to go up. If the temperature goes down, there's less speed, so that's less and weaker collisions, and so that's going to cause the pressure to go down. Okay. At this point, you can go ahead and go out of this video again and go look at Schoology, and this time you're going to go look at the Gay-Lussac's demo, okay, which is egg in a flask. Right, so here's an example of how you might solve some problems having to do with Gay-Lussac's law. It says, at a constant volume and number of particles, a gas has a pressure of 1.5 atmospheres and a temperature of 10 degrees Celsius. If the temperature is raised to 100 degrees Celsius, what is the new pressure? All right, so for the first time we have some temperatures involved. And as we learned yesterday when we're doing gas laws, temperatures involved mean that we need to change things into Kelvin. So the very first thing I'm going to do is I'm going to change all of my temperatures in here to Kelvin by taking and adding 273. So 10 plus 273 equals 283 Kelvin. And this one is going to be 100 plus 273, and that equals 373 Kelvin. Okay, so now that I've got them in Kelvin terms, I can go ahead and I can use our equations. So here we go. P1 over T1 equals P2 over T2. Okay. Do we know what the first pressure is? Yes, we do. It's 1.5 atmospheres. And we put that over the temperature that goes with it, which is 10 Celsius or 283 Kelvin. And that is equal to our new pressure, which we don't know, right? That's what they're asking for. And our new temperature, which is 373 Kelvin. Okay. At this point, there's lots of different algebra that you can use in order to be able to solve for P2. But the easiest one for me is always going to be, let's do cross multiply and divide. So I'm going to cross multiply and divide here, and we're going to end up with 283K times P2 equals 373K times 1.5 ATM. Okay. Now it's just like the equations that we used for Boyle's law. So to solve for P2, we're going to go ahead and we are going to divide both sides by 283K. 283 cancels on that side. So I end up with a P2 equals 373 times 1.5 divided by 283, which is 1.98 ATM. All right, now a chance for you to try. Go ahead and see if you can solve this problem, and when you're done, come back and check your answers with me. Okay, to solve this one again, I know that temperature is going to be involved. So the very first thing I need to do is make sure that I go ahead and convert my temperature. I only have one here, that's 25 Celsius. So I'm going to go 25 plus 273 gives me 298 Kelvin. Okay, so we'll go ahead and we'll do that. Then I can go ahead and I can start using my equation. So we'll go P1 over T1 equals P2 over T2. So do we know the first pressure? Yes, we do. It's 6 atmospheres. Do we know the temperature that goes along with that? Yes, we do. It's 298 Kelvin. Then we look and see if we can figure out what the new pressure is. Oh, we do. That's 3 atmospheres. And so that means that it must be the new temperature that we're trying to find, and indeed it is. What temperature does the gas need to be? Okay, so just like we did on the previous problem, I need to solve for T2 now. And so again, the easiest way that I know how to do this is do some cross multiply and divide. So if I do that, I end up with 3 ATM times 298 Kelvin equals 6 ATM times T2. And we are going to solve for T2 here. So the way I do that is divide both sides by 6 atmospheres. 6 atmospheres cancels on that side. And so I end up with a final answer of T2 equals 3 times 298 times 6, which is 149 Kelvin. And there we go. The third law we have is Charles' law, which has to do with volume and temperature. So the question that goes along with this is, if we increase or decrease the temperature, what will happen to its volume and vice versa? So what's changing here? Temperature and volume. What's staying the same? The number of particles and the pressure. So you can sort of think about it this way. If I have a bunch of particles in here and I've got this piston that can move up and down and I start heating up these particles, well, they're going to start moving faster and bouncing into each other more. And as they do, that's going to create more pressure. And it's going to push up on the piston, increasing it until that pressure goes away. Okay, so again, that's how we keep the pressure the same, is by changing that volume. So well, the relationship here then is as temperature goes up, volume goes up. As temperature goes down, volume goes down. If we graph it, we once again get that nice straight linear relationship, which is a direct relationship. And we can use the equation V1 over T1 equals V2 over T2. Why does it work? Okay, well, as I said, more temperature equals more speed. And so what has to happen is in order to keep the pressure constant, the volume has to increase to keep collisions the same. Otherwise, the collisions would be more. If there's less temp, there's less speed, so the volume has to decrease to keep collisions the same. Again, constant pressure. Take a moment at this one and go ahead and leave this video and go look at the demo video for Charles' Law. This will be balloon in a flask. All right, so now we can go ahead and we can deal with the mathematics of Charles's law. So at a constant pressure and number of particles, a gas has a volume of 10 degrees Celsius. And if the temperature is raised to 100 degrees Celsius, what is the new volume? All right, and so for this particular one, again, we're dealing with temperatures. So the very first thing I want to do is convert those temperatures to Kelvin by adding 273. So this becomes 283 Kelvin, and this becomes 373 Kelvin. All right, now we can go ahead and we can work out our equations. So V1 over T1 equals V2 over T2. In this one, do we know the initial volume? We do. It's 2 liters. Do we know the initial temperature? Yes, it's 283 Kelvin. Do we know the new volume? Nope, that is what they're asking us for. Do we know the new temperature? Yes, 373 Kelvin. Okay, so just like before, again, we have a situation here. Easiest way to solve this is going to be for us to cross multiply and divide. And so we'll go ahead and do that. And so if I do that, I get 2 liters times 373K equals 283K times V2. Okay. Way that we solve for this is to go ahead and divide both sides by 283K so we can get V2 by itself. And if I do that, I end up with a final new volume of 2.64 liters. All right, another U-try problem. The constant pressure and number of particles, a gas has a volume of 6 liters and a temperature of 25 Celsius. If you want to make the volume be 12 liters, what temperature does the gas need to be? You go ahead and try working on this, and then we'll come back together in a few minutes for you to be able to see how the answer works out. All right, here we go. First thing, I want to change that temperature. So 25 Celsius plus 273 gives me 298K. Now I'm going to go ahead and we are going to make our equation out here. So the first volume is 6 liters. First temperature is 298 Kelvin. And that's equal to our new volume, which is 12 liters, and our new temperature, which we don't know, right? What temperature does it need to be? Good. So again, just like we have been, we're going to go ahead and we are going to cross multiply and divide here. So cross multiply gives us 298K times 12 liters equals 6 liters times T2. Take both sides and divide them both by 6 liters. So it cancels out. And we end up with an answer of T2 equals 596 Kelvin. The last law that we have is Avogadro's law. And this is actually what led to Avogadro's number. And this idea is that if we increase or decrease the number of particles, what will happen to its volume and vice versa. So now we have the number of particles and the volume changing, pressure and temperature staying the same. All right, so we can imagine if I have a particle or a container here and I have some gas particles in it, and then I start adding more gas particles in there, that means they're going to start colliding more often, and that will increase the pressure. Well, in order to keep the pressure the same, because we want to keep it constant, we're going to have to go ahead and expand the space to keep the number of collisions the same. So in this particular case, we do have, as the number of particles goes up, the volume goes up. As the number of particles goes down, the volume goes down. If we go ahead and we graph that out, we get that beautiful direct relationship again. And so our equation becomes V1 over N1 equals V2 over N2. So again, why does this work? Okay, well, if there's more particles, that means there's more collisions. So in order to keep the collisions the same, you got to give them more space. Otherwise, you won't have constant pressure. Same thing, if we have less particles, there's less collisions. So again, if we want to keep the collisions the same, we got to reduce the volume in order to keep that constant pressure. Okay. Last one here for you to go check out. Go check out the demo for Avogadro. All right, so here's how we mathematically deal with Avogadro's law. No temperatures involved in this one, so we can go ahead and we can just start with the equation. V1 over N1 equals V2 over N2. And we're looking at this problem for a volume. Oh, we got one, 2 liters. And is there the number of moles that goes along with that is 3 moles. Okay. And we're going to go ahead and it says what is the new volume is our question. So that becomes V2. And if we add 6 moles of gas, oh, they're trying to trick us out here a little bit. If I had 3 moles and I add 6 moles, that gives me 9 moles. Okay, so I add 9 moles of gas, or 6 moles of gas, giving me 9 moles, and this is what I'm left with. Okay, so now we can go ahead and we can, just as we have been, cross multiply and divide. And when I do that, I end up with 3 moles times V2 equals 2 liters times 9 moles. Solving that, for V2, I divide both sides by 3 moles. And when I get done with that, I'm going to end up with a new volume of 6 liters. Your turn to try. At a constant pressure and temperature, a gas has a volume of 6 liters and contains 5 moles of gas. If you want to make the volume be 18 liters, how many moles of gas does there need to be? Give it a try, and when you're done, come back. All right, so for this one, we're once again going to use our equation. V1 over N1 equals V2 over N2. Okay. Do we know the first volume? We do. It's 6 liters. Do we know the number of moles that goes along with that? Yes, it's 5 moles. Do we know the new volume? Yes, we do. It's 18 liters. Do we know the new number of moles? No, we do not. So that's N2. Following the same pattern we have been, we cross multiply and divide. So this gives us 5 moles times 18 liters equals 6 liters times N2. Okay, in order to solve that, I'm going to divide both sides by 6 liters. Cancels on this side, and so we end up with N2 equals 15 moles. All right, so a couple things that we want to make sure that we get out of today's notes. One, that we get out an understanding of how pressure, volume, number of particles, and temperature change if we change one of the others. The second thing that we need to know and understand is being able to actually do the math for the gas law. Hope this was helpful. Thanks.